am recording again. All right, so there are 4 new projects. WinDebug Preview, 3 of them. Source level debugging, which is very nice. We'll compile some code from C, and you can see you can work from the source code instead of the assembly code. And then kernel debugging on 1 machine, and then kernel debugging across 2 machines in Azure, which worked, and I was very pleased to see it. So you can actually put breakpoints in and see what's going on in the code. And then when I published these projects on Twitter, Dan Kaminsky told me about this tool, API Monitor, which I didn't know about, which is very nice. And so that's why there's 4 projects, because other people are helping pitch in. And so let me just talk about these. I don't know if they're worth doing live demos, but it's certainly worth talking about them. So they're all down here, 431, 2, and 3, and the other one's up there. So here's 431. So what you have to compile code. So if you have the Flare VM, which I highly recommend, then you should make, you already have the Microsoft Visual C++ build tools version 2015, which is fine. So you make a simple function here. I just got this from a Microsoft tutorial. You don't need to import any libraries at all. It doesn't even have any output. It just has some integer variables. So you make some variables. This one is 2, this one is 0. Then you call a function, and this function will eventually divide by 0 and crash. That's the only point of this thing. So you can compile this thing. This is the standard Microsoft compiling EHSC. I looked it up and forgot what it is, but that's a normal Microsoft compilation. And you end up with an object file and then an executable file from it. And this is, of course, what you run. So you can run myapp.exe. And so you can load it in WinDebug. If you have Windows 10 of any kind, and what I did was use Windows 10 on Azure, which I recommend for the City College students, you can get a free Azure service. If not, you can run it locally. So you load this product, WinDebug Preview, and you can now just launch the executable inside here. And it will run and hit a breakpoint. CC is the typical interrupt 3 breakpoint that you see here. And so it loads a few libraries, so and a couple kernel 32, kernel base, and app help, these dills, and then it stops. So now you can find the symbols. If you examine Myappmain, you'll find there are no symbols here. It doesn't find anything in there. That's looking for named processes in your application. And this is because the way you the way you compiled it, there were no modules. So if you do LM, you'll see loaded modules. NTDill, the Microsoft library, has modules and has labels, and the symbols are in this PDB file. That's the Microsoft format for debugging. And like I say, Microsoft does provide debugging symbols for their products, but it's not here. So if you want it, you have to go back and recompile it with this ZI switch. That will put the symbols in there. So now when you compile it, it will create these PDB files for both the app and for something else. I think this is the redistributable C++ that you're using. Anyway, now you have symbols. And like I said, in older tutorials, they will all tell you you now have to load the symbols, but this product is smart enough to just find them automatically. So now when you load it, it's going to find this, it's going to load with the symbols. And now if you look inside your app for things called main, it's going to find all these symbols in there with main, including this one, which is the main entry point, Myappmain, and then other things that have main in it. So now you have written code and you have symbols. And not only that, you can set a breakpoint and run. And when you do, it's going to show you the C++ source code. And you can now debug it and put breakpoints in the source code. And it's even nicer than that. It starts here. This is what it does when you load it. It loads and then puts a breakpoint there immediately, right at the start in the main function. And it puts your variables right down here. It automatically notices that this has variables A and B, and it shows you their values. And at this point, in this highlighted point with the red arrow, this is before we've assigned values to them. So one of the many weaknesses of C that leads to a lot of vulnerabilities we exploit in the vulnerability exploitation class is these things have values even before you assign values. before you assign values, they show you information from the stack, just whatever happened to be there. And if you look at format string vulnerabilities, you can exploit this. Anyway, so right now, these have random uninitialized values. And if you step through the code, you can just click step into. It's just right up here, step into, and step over and step out, just like in the other debuggers we've used. So you can step into, go down a couple steps, it'll execute this one, long A equals 2, and now that variable has switched to a value of 2 instead of some random number. And you can just go ahead, you can step through the whole thing, and when you get to this line, which divides by 0, you'll get an error showing that integer divide by 0. So it's really very nice. All right, and when you have a crash like this, there's an analyze function in WinDebug that will analyze the crash, and it will show you the source code and tell you what happened and give you exception codes and so on. So it's really very nice to debug code you wrote, where you have the source code and the symbols. So that's a useful skill to know if you're going to write your own code. All right, and then kernel debugging on one machine for starters. So you'll use one machine, and I use the Flare VM, although I don't suppose you really need it very much. The only thing, I use CFF Explorer once, but you could skip that step if you want to. Here's the structure we've talked about. You have an application in Userland. It calls kernel32dil, which calls ntdil. This is the native API that normal functions don't use. And then that jumps into kernel mode, into NT. And then that connects to kernel data structures and drivers to do whatever you're trying to do to the hardware. So we're going to explore NTOS kernel, which you cannot explore from Userland. Now, you can look at that file. It is one executable file on your disk. That is the Windows kernel. The whole thing is there, and you can just open it like any other exe, and you can open it with CFF Explorer, which is one of the code exploration tools in the Flare VM. And you can see it's got an export directory, and here's some functions like Alpc, create security context, and a long list. You can see the scroll bar, a long list of other functions are here. And so that's all the kernel routines being exported from that file. So once you have WinDebug preview, you can do local debugging. Now, in the old days, you had to download a sysinternals tool and run livekd to do this, but this seems to be built into Windows now. All you have to do is turn on, in BCD edit, turn on debugging, and then set debug settings to local. And that will permit you to locally debug the kernel on this one machine. Although, of course, you cannot stop the kernel or use breakpoints, but you can examine it. Then all you have to do is reboot, which is very nice. You reboot, now you can start your Windows WinDebug, and when you go to start debugging, you can attach to the kernel. And when you go over here, here are your choices. These are the old choices where you had to go through a serial port or something ridiculous like a certain kind of USB and stuff, but we're going to use local. There you don't need any network connection at all, and that will debug the kernel on this one machine locally. So when you do it, now you can load modules. And notice it already has the symbols for NT. So it shows you the NT being loaded and a couple other things here that are not loaded. So you see Windows NT, and you can just click the NT link, and it will now show you more information about Windows NT. You can browse all global symbols or just the functions or the data, and you can just click these links to get some of it done with the mouse, although to get much done, you really have to use the command line. For example, here's the kind of stuff. When Microsoft starts moving to a graphic environment, for some reason, they don't go far enough. Now, OllyDebug, you can really use the mouse and get work done. Microsoft puts a couple functions in that don't work right. So it's surprising how much they don't bother to make this work. For example, if I browse functions, I'm going to see all the NT kernel functions, of which there are thousands. So what does it do? It breaks them up into alphabetical lists, each one list way too long to see. So when you scroll back up, you can click a link, and then you'll have a list of all the A's or a list of all the B's. So it's not really useful yet, which is really surprising. You know, they could have given me a scroll bar or something. Anyway, that's what they've done. So now I have all the functions. Here's the addresses for them. Notice all the kernel addresses start with FFFF. That's where the kernel is. We'll see more of that later. And here's all the functions. And one of these is the one that we saw being up here in CFF Explorer. One of them up here was Alpc, create security context. And that is on my list here. Yeah, ALPC create security context. There it is. So you're just seeing the same list of information that you saw by looking at the exe, but this is now looking in memory at the loaded module. Up here at these high addresses of memory where the kernel lives. So, all right. And by the way, when you do click these little things, all it does is execute this command for you. So when you click the A, all it does is execute this command, x/d/f_nt a*, which is a fairly simple way to make a GUI. This, by the way, is how Windows used to work in Windows 3.1. You would start with MS-DOS, you would type win, it would show you a graphical display, and when you clicked things, it would just be creating the MS-DOS command and executing it behind the scenes. Anyway, so you got help, of course. You can go to local help, and it will show you how to use these commands like X and such. This is where you go to learn all the details of how to use Windows. So you've got a flag to look for here, find a function that has warbird in it in the kernel. And then you can disassemble functions. With UF will unassemble a function, and you just give it a specifier to your function. So here's the one we talked about quite a bit, NT create file. That is the whole thing. There's really not much to it. All this does is set a bunch of stuff, put a bunch of stuff on the stack in the right place. It's putting all these things in addresses from the RSP, which is the stack pointer. So it's just filling the stack with data in the right format. This is all this mess is putting a data structure in memory, and then it calls another function, IOP create file. So this is really just a stub that reformats the data and then sends it off to another function. All right, you can search memory. So I can search starting at this label and going for the next 100 bytes, and I can search for this pattern of bytes. I did that just because you can see it here. Here's the addresses of these commands, and here's the raw bytes. So right here you have 42, let's see, yeah, 44, 24, 78. You have it right there. So just so I can practice using the commands, I'm going to look for that. Starting here and looking for 100 bytes, looking for that pattern of bytes, and it finds it right here. 44, 24, 40 is right there, which is at 003 FDF4, which is here. It found this one down here, 44, 24, 40. All right. So that shows you how you can find things. You can also search for strings. SS minus SA will just find all strings that are 3 characters long or more, and all these are sort of meaningless gibberish. And you can put an L6 here, and it'll look for strings that have length 6 or more, which again gives you less junk. And anyway, the string magic appears just once in the whole kernel, so you can find that. That's a flag. All right. And all right, then you've got, you can display NT. This is the NTOS kernel, which is a Windows executable file. They all start MZ. They all have this string. This program cannot be run in DOS mode, and so on. So that's, you can display a raw file there. You can examine data structures like we did here. This shows you the NT file object. And you can view processes. T-list gives you a list of all the running processes on your machine, just like Task Manager would. You can examine more details about one process with the process command. And it gives you a lot, like all the DILs it's loaded and so on, more information about a process. And here you can view devices and drivers. You know, you just get to try a few of these commands, and then there's another flag to find. So when you're done, you can disable debugging and restart your machine, and you'll be back where you started. So that's debugging on one machine, where all you're doing is looking at things. And I thought that was as far as we would go, but I tried this, and it worked on Azure, which surprised me, because when I tried this with real machines in the lab back in the days of Windows 8, it didn't work very well at all. But now Microsoft has got it working. So you make 2 Windows 10 machines on Azure, or you can run them locally anywhere, but I did them on Azure. And so you've already learned how to make a machine just with add in your Azure account, and you're using fake money, and you just make 2 machines. So I made one called Windows 10 and one called Windows 10 Target. And they really don't have to have much more than just Windows 10, but this one, in fact, is the Flare VM. That one's just a naked Windows 10 machine. Right now, make sure they're both on the same network so they can see each other. By default, it'll create a separate subnet for each machine. So you have to go into virtual networking and check this subnet name. You can click it and change it. Make sure they're both in the same subnet, and then these machines can see each other. This is the same trick I used on the Google Cloud, and it's very nice. If you put two machines in the same subnet, then there's no cloud firewall between them. They can see each other. We don't have to keep going and putting exceptions in the firewall, which is very nice. So when you're done with that, then you'll have two machines on the same subnet, so they'll both have similar addresses, and all you have to do is turn off the Windows firewall on the target. So you go into the settings and turn off the firewall, and now the target can be accessed from the other machine without any restriction, which is what we want. So if you go to ipconfig, you'll find your addresses. Oops, somehow the wrong figure there, but 10.0.0.4 on one machine and 10.0.0.5 on the other. So you can ping from one machine to the other. You can ping from one of your machines is called the host. That's the one that's going to run WinDebug. The other is the target. That's going to have kernel debugging, so it will stop when it hits breakpoints. And the target machine is the one where you have to turn off the firewall. So you make sure you can ping that one from the host. And now you set up network debugging, which is very simple. You turn on debugging with bcdedit debug on. This test signing lets you use unsigned drivers, which I thought I was going to use in this project, but I didn't get that far. So that is harmless, but it's not necessary. This is the necessary one. This is the one that does debugging over the network. And you give it the IP address of your other machine, the one that is going to control it, 10.0.0.4. You specify a port to listen on, and then you have a key. And the key has to be 4 alphabetic or numerical things separated by dots, and you can only use numbers and lowercase letters. So I just used flapjack, dog, frog. It doesn't matter, but you have to have 4 objects with 3 dots, and you can't use capital letters or spaces or special characters. Anyway, this is a security feature, and what's going to happen is you can check the settings with debug settings, and it will show you your settings, and then you restart the machine, and it will restart in debugging mode. Now, you might as well prepare the other machine first. So you go to the other machine and run WinDebug preview. Again, you attach to the kernel, but now instead of local, you go to the net tab, and you have to fill in the port number, the key, and the IP address of the other machine. And this is what's really wonderful. You used to have to get a special serial cable, and it was really a drag because modern hardware didn't do it very well at all, and the virtual simulation of it didn't work very well at all. This actually works over networks, although it does not send ordinary IP packets that you can see, and it does not open listening ports you can see. So it's in fact sending some kind of weird network traffic at a lower level. But it does come in on a port and an IP address and with a security key. So now you prepare this one, ready to control the other machine. You restart the target computer, which you can do with this command line. And then when it restarts, you can connect with RDP again. And when you look at the Ethernet, it'll have this label here on the Ethernet adapter. Now your adapter is running in some different mode, listening for kernel debug symbols, which, like I say, is very strange. You will not see an open listening port the normal way you do it. Anyway, all right, so here, now your host is going to show it connected. Kernel debugger connection established. Now it's going to show you some information about the machine. It's going to find the symbol searches and so on, which Windows 10 it's running, which kernel version it has, and now your debuggy is running. So at this point, you cannot issue any debugging commands because the target is running. In order to run commands, you have to break here, which will stop the target machine, and then you can issue debugging commands. So you hit break, and it will take a few seconds to take effect, and then you'll see this, which is say you pressed either Control C or Control break. This is not a bug or a system crash because your other machine is now frozen, and your RDP connection is going to time out and hang up on you. It's going to look like a crash because it's not listening to all the processes on it are no longer running. You can now load modules. When you load modules, you're going to see a lot more modules in this case. But notice they don't have symbols. NTDill has symbols, and NT has symbols, but all the rest of these modules written by Microsoft don't have symbols, which is kind of rude, right? I mean, we might want to look in those modules, and without symbols, it's going to be unpleasant, so you can get them. You just execute these commands. Sim noisy just lets us see the progress. Reload /F. reloads the symbols, and after you run them, it'll take a couple minutes to download them all, and then you'll have symbols for every bloomin' module. It's wonderful. This is why I say Microsoft might as well be open source for all practical purposes. You can totally see how every module works in here. And all right, so now you can examine, for example, the file info module is one of these modules. And so you can look in there, see a lot of symbols. Here's the ones referring to memory. Here's file info. I noticed this one called memset. I was playing with this quite a bit just to try to catch various options. And one thing I noticed is many modules have a memset routine, and it's almost always called. So if you put breakpoints on the memset routine, you can get it to break when doing things, and then you can look at the call stack, which is what we're going to do here. So we're going to put a breakpoint on the memcopy routine. That worked here. Memset probably would have worked too. And now you can do it in the GUI. This will set the breakpoints. You can then go on View and hit breakpoints, and it will show you a tab down here showing you your breakpoint. So I have a breakpoint on file info memcopy. Okay, now I can run it. And when I run it, it will hit go right here, go. It'll run, it'll immediately hit because this breakpoint is on a routine that's used frequently by the operating system when it's just sitting there doing nothing. So it will hit, it will stop. And then I used K to see the stack. And here is the stack. And this is where you really learn a lot about Windows. Here's a userland process. Read it from the bottom. This is the process that was running in userland, whatever it is, that called crypt32, which is a DIL, and that did a whole bunch of cryptography things here like certificate and stuff. Then it called kernel base called ntdil, and that called NT. And notice the addresses. FFF is the kernel. Those are at high memory. Userland is down here at 000. So here I am in userland. Userland, ntdil is the userland entry into the kernel. That called a kernel routine. Now I'm in kernel land. Now I call a whole series of kernel routines in Windows NT, and then that calls FLT-MGR, and that calls file info, and here it hit my breakpoint. So you can totally see exactly the path that led you here. And it's very nice if you want to understand how Windows works. And of course, if you wanted to debug problems in Windows, which is what this is for, you could see exactly which modules are being called and break it and explore all the way back. So that's what's going on here. And here's a diagram I found explaining this. In 64-bit Windows, you cannot actually address 2 to the 64 bytes of memory, which doesn't matter. Nobody can afford that anyway. Modern hardware only uses 48 bits for addresses, and so it's split. There's a region all starting with zeros, which is used for userland, and a region all starting with Fs, which is kernel land, and a huge space in the middle that is not used in hardware at the moment. So that's how it works. So you can easily tell from the address whether you're in userland or kernel land. So now you can remove the breakpoint, which you can just do in the GUI. Up here, you see breakpoints. That's why this little bit of it is very nice, sort of like OllyDebug. One of these windows, you see breakpoints. I guess I've gone too far back. There. You can just right-click and remove a breakpoint, which is nice. So these buttons help a little bit. You can remove breakpoints and see them there. You can use Go on the Home tab to run the things. You don't have to do everything with command line tools, but you know, they don't really do much more than a command line. So anyway, all right, so here you're going to put a breakpoint in RDP-DR. RDP is Remote Desktop Protocol. That's what we're using to control our machines. So as you can imagine, if you put something in RDP, it is not going to hit just during normal running. But when you try to reconnect with RDP to your machine, it will run these RDPs, so you're able to put a breakpoint there and stop it, and you can see the call stack getting you into RDP, dir, memset, and that's a way to see a flag. So you can move the breakpoint. Now we're going to watch file creation. So I put a breakpoint at the start of create file A in kernel base and go, and it should hit anyway because Windows machines are constantly creating files all the time. If it doesn't, then you just connect via RDP, and the RDP connection will create some files. So you'll end up with a breakpoint hit, and now you can examine the stack at the breakpoint. DB, RSP, this shows you the data in the stack, And notice how here's stack variables, and there's the name of the file that's being created. See Windows System 32. So you can read a file name just right there on the stack, which is common when you're calling a create file routine. You ought to imagine that one or the other of the parameters on the stack will have the file name, and they do. So you can see where this is. Here's the start of the stack, which is RSP. This is plus 10, 20, 30, 48. Takes you to the start of this. So RSP plus 48 in hexadecimal gets me to the string. So you can now use DA at RSP plus 48 to dump it more precisely, and that'll give you just the name of the file. So now you can make an automated task, which is very nice. Here it is. You can set a breakpoint, a kernel-based create file A, and then you can put some commands to execute every time it happens right here. And the command is dump the name of the file and then run again. So when you start it running now, it's going to continue running, and it's just going to put all the file names scrolling by up here that it opens. You can have continuous monitoring of all the file names it opens. This is very nice. I know how to do this for Linux and GDB, and it's really great to be able to do it in Windows. So you can just write little scripts that are not too hard to write, and you can make a living monitor for any part of your Windows machine you want to monitor. So it's good, clean fun. And so down here, there's a way to get a, when you open a network stage, you'll see a certain file open, and that's your flag, and you can disable debugging. So that's the joy of debugging. And the last thing I want to point you to is this other project up here, API Monitor. This is, I think, just Userland. I don't think I'm worried about Kernel Mad, but this is a product I didn't know about, and it's bloody awesome. You install this thing on a Windows 10 machine. You only need one machine, and now you can set a monitoring on a, it'll show you all the modules. You can look for all the modules on your machine here. And so if you look for create file, it'll find everything with create file, and you can just tell it which functions to monitor. So monitor create file A in kernel 32, create file W in kernel 32, and NT create file in NTDIL. You can just check the functions it's going to examine. And then when you launch Notepad, you can launch it here with a command line. Here's the program, Notepad. Then there's the name of the file it's going to create, my new file, and run that. And then it's going to show you right here all the system calls. So here's the modules and particular functions in the API that we're monitoring. Here's the process we're monitoring, which is Notepad. Here's what it caught. This is very much like Process Monitor, which we've been using before. But it gives you a lot more than Process Monitor. It gives you all the calls, and it gives you all the parameters. So you can click, here's kernel-based calling NT create file, and here's create file W, and so on, all the calls. And here, when you click on this, it shows you the entire stack laid out here. Here's all the parameters, and you can see the values, so you can highlight the right value and just see the name of the file right there. This is bloody awesome. So you can really go to town with this. So there's a flag to get on this Notepad thing, and they had some really old tutorials from like 2001 that I didn't think were worth it, but I found another one that's really great. You can steal passwords from the RDP connector here. So if you connect to another machine, like another Azure machine, you have to give it an IP address and your username and get ready to connect. And then you can monitor API calls here. So you go in the running processes down here. This connection module, RDP, is got a name which comes from Microsoft's old name for it, which was Terminal Services Client. So it's called mstsc.exe. If you monitor this process and then look at these modules in the crypt32.dil, crypt protect memory and crypt unprotect memory, those are what's used to prepare passwords and encrypt them on the way to go out the network card. So when you log in, you will find those calls here, and one of those calls has your password right there in plain text. So this is very nice. And this is, of course, why you use things like keyloggers and such. If I have malware on your machine, I can catch data before it gets encrypted. And this is reminiscent of the Target hack, where they stole the credit card numbers from payment terminals before they were sent over the network. Anyway, this is a great product, and you can really see a nice graphical presentation of how Windows works, and you can examine it with processes. So one of the old projects, which I didn't think was worth giving you, was how to defeat copy protection on copy protected products. They'd have like a trial version and a date, and you could just find the API call and change the date and things like that in here. So it's a very good way to see the Windows API, and that's something to learn. So anyway, those are the projects I wanted to show you. I guess it's not necessary to do any of them live, but pick some of them to do. So this class, like I say, is insane. There's far more homework than you need to do. So the official plan I had was this stuff up here. So do that if you like. But if you feel like moving to the more modern stuff, go down to this Flare VM stuff, and you'll be doing the latest stuff on the latest Windows 10 and on Azure, which are the modern ways to do it. There's Ghidra if you really want to get into that level of reverse engineering. And there's someplace I've got the assembler here. If you want to learn assembler, there's just many things to learn here. Like I say, in the future, this class will fork into like at least one more additional class. I think definitely one class just on Windows internals, not even really focusing on malware anymore. Anyway, I'm going to stop this video, and then I'll try and answer some of these questions.